My name is Didier Henrion, and it's my pleasure to give this second lecture within the POEMA European Network. As promised during the first lecture, I'll be speaking about dynamics, and I will speak about the use of the moment sum of squares or LAAS hierarchy to solve a particular problem arising in dynamical systems and discrete time dynamical systems. So I will make 2 breaks during the talk to allow the audience to ask questions via the chat. At the end of the lecture, I will get back to the exercises of the first lecture. The PDF files with solutions, written solutions to the exercises is already available on the POEMA website for you to download. So if you want to have a look, please go there, and I will comment on these written solutions at the end of this lecture. And you will be given the opportunity to ask further questions using the chat as well. So let me start with the second lecture. The slides also of this second lecture are also available on the website. So I'll be speaking about dynamical systems and estimation of positively invariant sets. And I will follow the same strategy as the last week, mainly given a nonlinear non-convex problem, here positive invariant set estimation. I will first reformulate this as a linear problem at the price of enlarging the space of solutions. As last week, we'll see that we'll have to go to spaces of probability measures. Then the second step will consist of solving approximately the linear program with a family or hierarchy of optimization problems of increasing sizes. The third step, which is where most of the theoretical results can be found, will be about ensuring convergence of the hierarchy. So last week, in the scope of polynomial optimization, we saw that generically the original non-convex nonlinear polynomial optimization problem can be solved at a finite relaxation size at the price of solving a finite dimensional convex optimization problem. Today, we'll see that it's in general not possible for positively invariant set estimation. So we'll have to go asymptotically, and we'll construct a family of approximations with increasing quality. And again, we'll see that duality and conic duality will prove essential as an ingredient towards the goal. So the positively invariant set estimation that will keep us busy today is the following. So it's a maximal positively invariant set, MPI set, for a discrete time dynamical system. So it's defined as follows. It's defined as a set X sub I for invariant, of initial states X0 that remain within a given set capital X during iterations given by a polynomial map. So this notation X sub t means that X is a vector of Rn indexed respect to time. So time instance, t equals 0, 1, 2, etc. And at each time instant, the next iterate is obtained as a function of the previous iterate just by applying the map F. So F is a polynomial map from Rn to Rn. And capital X is a bounded basic semi-algebraic set of the same kind we saw during the first lecture. So both F and capital X are given. Capital X is explicitly given as an intersection of finitely many polynomial superlevel sets. So in other words, as a set of vectors x in Rn such that G sub k of x are all non-negative for k running within a discrete finite set, and with the G sub k being polynomials of x, so real valued multivariate polynomials. So again, it is a set of initial conditions that remain in capital X forever during the iterations. So it turns out that even in the simplest cases, for example, when the dimension is 2 and f is just a degree 2 polynomial, the geometry of this MPI set can be very complicated. So here is an example of, on the next slide, of the MPI set for a quadratic map. This is a Julia set. It has a fractal structure, as you can see, and it's extremely complicated. So we'll not be able to compute or describe this set explicitly in general, and we'll be already happy with a family of approximations of this set with a control of the quality of the approximation. The more we can compute, the better will be the approximation. So this is the contents of this next slide. We content ourselves with approximations of the MPI in such a way that the quality of the approximation improves at the price of more computation. And here I'm already describing what will be explained during the lecture. This is the output of the algorithm I will describe. So this moment sum of squares or Lasserre hierarchy will generate a family of approximations to the MPI from the outside. So outer approximations, they are denoted capital X sub I sub R. They are such that all of them for all R contain the MPI. And they are described as a polynomial superlevel set, the set of vectors X such that a given polynomial V sub R is non-negative, while R is an integer referring to the degree of the polynomial. So we let this degree R increase, and the larger R will be, the better will be the approximation, and in such a way that when R tends to infinity, we have convergence guarantees, and the best convergence guarantee we could think of in this context, given the potentially intricate geometry of the MPI, is convergence in the Lebesgue measure or in volume. So we'll actually prove that this family of outer approximations, they converge in volume when degree R goes to infinity. So this is the outcome, the output of the algorithm. Now I will tell you how we compute these objects. I will follow the promised program, these 3 steps. So the first one to start with is the linear reformulation. And you may recall that for polynomial optimization, the main idea was to reformulate the original nonlinear, non-convex problem as a linear, hence convex program, an LP, but instead of working on Euclidean space Rn, we had to work on probability measures on Rn, so infinite dimensional space. And you may also recall that an optimal solution to the infinite dimensional LP was any Dirac measure concentrated at any optimal solution of the polynomial optimization problem. In the context of dynamical systems, we'll proceed exactly the same way. The only difference is that the probability measure will now depend on time. So given a trajectory, a map from time to the iterates, we define mu sub t as a measure of the state space, the measure of small x, which is a Dirac measure concentrated at the value of x at time t. So I'm sorry here, there is a little typo. This is expected to be x of t, x sub t. Equivalently, this is an equivalent definition using Borel sigma algebras of the set of states, capital X. Mu t of A is the indicator function of A, which is equal to 1 when the argument of the function belongs to the set A and 0 otherwise. Here 2x of t should be x sub t to be consistent with the notation. So once this is defined, at each given time t, we let time iterate. And given an initial condition x0 and the scalar number between 0 and 1, alpha, called the discount factor, we define the discounted occupation measure as the weighted sum of all measures mu t defined in the previous slide. They depend on x0 just because there are Dirac measures at the iterates, and the iterates xt depend obviously on x0. And they're weighted in the sense that I take the sum, but with the alpha to the power of t to define now an object which does not depend on t anymore, this occupation measure, mu of dx. This notation here, it is a probabilistic notation. It just means that mu depends on x0. The mass of mu, so the integral of mu over the whole domain, is by definition the sum of the masses of all these measures, since each of them for each given t is a probability measure. I'm just summing up powers of alpha, and then I get this number. Since alpha is between 0 and 1 strictly, this is a finite number. So here you see the relevance of introducing this discount factor. It just makes the mass of the occupation measure finite. So now suppose that the initial condition x0 is not a given vector in Rn, but not a single point in Rn, but a distribution of mass in capital X. In other words, a probability measure that I will denote mu0 on X. We can then just take the I'm sorry about there is talking, and this is very disturbing. Lynn, maybe you can have a look and unmute. It's very annoying. Thank you. So I defined the average discounted occupation just by taking weighted combinations according to the mass distribution of mu0 of this occupation measure defined previously. So it's a convex combination, and where the weight distribution is ruled by this probability measure mu0. This I call the average discounted occupation measure, or for short, occupation measure. So it does not depend on time anymore, and it does not depend on the initial condition anymore, just implicitly via this integration. So once this has been defined, we can derive an equation linking the average discounted occupation measure mu and the initial measure mu0. So consider a trajectory xt staying in capital X. Then for every observable or every test function v, continuous function of x, we can compute this quantity, the integral of v against mu, the mu which depends on x0. So this is by definition of the Dirac measure. Remember, this is a weighted combination of Dirac measures with weights the alpha t. So this is just a weighted combination of point evaluations at the test function at these values xt. So the sum over t of alpha t v of xt, which can be rewritten just by extracting the initial value here and factoring respect to alpha the remaining term as follows, with the index shift here. And here, since I have an index shift, I use the equation of the dynamics. Remember that x of t plus 1 is equal to f of xt. So I just replace here xt plus 1 by f of xt. And now I'm back into business, because this weighted combination is nothing but the integral of v of x of v of f of x against mu depending on x0. And just like here, it was the case. Now I do what I did at the end, at the bottom of my previous slide. I just integrate on both sides of the equation sign respect to the distribution of initial states. So integrate respect to mu0 of x0. And what I get is that on the left, I have the integral of v against my average discounted occupation measure, so integral of v against mu. Here I have just integral of v against the initial measure. And here I have the same integral as here. The only difference is here I have iteration of the dynamics. So this can be written in a little bit more concise way. So first, let me emphasize the fact that the equation now becomes linear in our defined object in mu0 and mu. These integrals, they can be written as duality brackets, just as we did last week. Integration of a continuous function against a measure can be written like that. And the same for the initial condition. And here I just write integral of v composed with f against mu. And if I want to isolate here on this duality the test function v, I have to define the action, which is F sharp on mu, I have to define an object which will be actually a linear map. No, not acting on V as before, but acting on mu. And these two maps, I will return to these maps in my next slide. They will be adjoint to each other. So by doing so, in the last line, you see that I can actually remove the test function and rewrite this mu equals mu0 plus alpha F sharp mu as a purely linear equation on measures without test functions. This equation, this linear equation, I will call the Liouville equation. So now let me have a look at these operators. So they have names. They are very classical objects in dynamical systems. So the first one is called the composition or pullback operator or the Koopman operator. And it is the adjoint to the Frobenius-Perron or push-forward operator, this F sharp. Adjoint in the sense we saw already in the previous slide, and that this holds for all test functions and all measures. Remember, this is my notation for a measure, a topological dual, two continuous functions on X. So it turns out, even though it is not the topic of my lecture, but there is a lot of work on that, it turns out that information on the behavior of my dynamical system can be inferred from the analysis of the spectrum of the eigenvalues of these linear operators. I will define another quantity here, which is actually the image of this operator. It's called the push-forward measure or the image measure. And the equivalent definition of this can be seen here. So given a measure mu, its image through the map F is defined here using the Borel sigma algebra as a measure of the preimage set. So the set of X such that f of X belongs to A, given A. And it turns out that the measures which are fixed point of the Frobenius-Perron operator, in other words, the eigenvector or eigenmeasure corresponding to the eigenvalue 1 of this operator, they are called invariant measures. So invariant measures are also very classical objects in dynamical systems. So here is a very classical example of a map. It's a scalar map from R to R. It's called a logistic map. And you see it's quadratic, degree 2 polynomial. It's defined on segment 0, 1 of the real line. And the first exercise for you is to derive analytically the expression of the image measure F sharp mu of a measure mu which is absolutely continuous respect to the Lebesgue measure with density or Radon-Nikodym derivative m of x. So for a measure which is absolutely continuous respect to Lebesgue with density m, find the formula for F sharp of mu for the image measure. Then the second question will be just to apply the formula obtained previously to the special case of the uniform measure. So this is the Lebesgue measure on the 0, 1 interval, and the density is equal to 1 everywhere. So the exercise consists of computing the image measure once and actually to iterate the operator again to compute the image of the image measure through the map F. The third question will be to prove that this particular measure, so a measure which is absolutely continuous with respect to Lebesgue, but which has this density here, turns out to be actually an invariant measure for this map. And the last question will be to prove that this measure, which is not absolutely continuous with respect to Lebesgue, this is a Dirac measure at 3/4, is also invariant. So as you may have suspected, invariant measures, they will play an important role in the characterization of positively invariant sets, just because the invariant measures, they will live on the subset of X, which is positively invariant. So before I give you the floor for the chat and the questions, I will just illustrate this logistic map geometrically. So here you see this red plot is a plot from X to f of X. So it's 4x times 1 minus x. This is exactly the equation of the map. And here the diagonal is just x equals x, so that the intersection point here is the set of points which are left invariant under one iteration. So fixed point of the quadratic map. And you see that here approximately we get something which is a little bit less than 0.8. Actually, that's the last question here of the exercise of the previous slide. The exact value is 3/4. So it's rather easy just by computing the root of this polynomial, which is a degree 2 polynomial equation, to prove that the fixed point is 3/4. So that the measure concentrated on this point is indeed invariant and belongs to the positively invariant set. Now, if I apply the iteration twice, f of f is a degree 2 polynomial, I get a degree 4 polynomial. And the fixed points, there are 4. The origin, which I forgot in my previous slide, was also a fixed point. But also these 2 new points here, this one and this one, and obviously the point I had before, 3/4. Again, we can find these numbers by finding the root of degree 2 polynomial. So it is degree 4, but since I have 2 roots, 0 and 3/4, I can factor it into the product of the degree 2 times a new degree 2 polynomial. And if I iterate again, I get points which are left invariant under the application of 3 times the map, a degree 8 polynomial to be solved. Okay, now, so this gives, this shows that actually there are many invariant measures, and actually there are infinitely many. And let me get back to the exercise. There are measures which are supported on finitely many points, but there are also other invariant measures that are not combinations of Dirac measures, that are not atomic. They are absolutely continuous. So it means that there is somehow a continuum of equilibria in that sense. And you may be familiar with the logistic map. Actually, if you plot the equilibria of the logistic map as a function of the growth rate here, the parameter k, so this is my abscissa, this is the value of k, you get this kind of picture, very interesting. So for example, if I take a value here, say 2.8, k equals 2.8, I observe that I have a single fixed point, which is x a little bit bigger than 0.6. And then when I have k bigger than 3, I have a bifurcation phenomenon. I got 2 fixed points. And if I go further, if I increase the growth rate, I've got this exponential number of Equilibria points, isolated points. And eventually I get this, this behavior, this continuum of Equilibria. We are here for the logistic map and the exercise in the case of, in the limit case of k equals 4. So as you can see, the geometry of these invariant measures is pretty intricate, just as the geometry of the MPI set can be, yet we'll be able to compute with these objects. And I will tell you more about it just after the first little break. So do you have questions on that part to share with us on the web and on the chat? No questions? Okay, don't hesitate. Once I resume, to post questions on the chat. I will then go through them during the second break and also at the end of the lecture. Last chance for questions for this first part. Okay, no questions. So let me start again. So you remember what I did was, let me get back. What I did is I started with this MPI set, and I defined these occupation measures, several of them here on this slide. And the key property that they have is that actually they are linked linearly. And somehow, instead of having to deal with a nonlinear problem, this nonlinear iteration, I have to deal with a linear equation on measures, what I call the Liouville equation. The measure, this equation measure is linear, and it involves an operator, which is the Frobenius-Perron operator, which somehow encodes the property of the map F. And the geometry of the system is also encoded in the image measure, especially those of the image measures which are invariant under application of the operator. And now that what we'll do is to play a little bit further and to look at the geometry of these measures, especially the geometry of their support. So I already started with a little example showing that fixed points and finite orbits of the dynamical system is in the invariant measures. And we can say actually much more. So again, to summarize the first part, instead of the nonlinear dynamical system, I have now a linear equation, this Liouville equation, defined on occupation measures. And for my API set, the support of the initial measure will be closely related to x sub I, to my API set, in the sense that is made precise in this lemma. So for any measure mu and mu0 that solves the Liouville equation, and such that their support is in capital X, then the support of mu0 will be in x sub I in the MPI set. So the support of a measure, intuitively, roughly speaking, it is the set of points to which the measure gives some non-zero mass. So more formally, it can be defined like that. So it means that the support of the initial measure is included into xi. And since we have freedom in the choice of mu0 here, you just have to satisfy this linear equation with mu. What we'll try to do is to make this support as large as possible. So in order to do that, we'll use optimization. So we'll consider a linear program which will consist of maximizing the mass of the initial measure subject to two constraints. The first constraint is that the measure satisfies the Liouville equation for some mu0 and mu. And the second constraint is that the measure mu0 is dominated by the Lebesgue measure. So let's see if I can remove that. So here, this equation means that mu0 is less than the Lebesgue measure, lambda on capital X. So in other words, if I take a subset, a set in the Borel sigma algebra, a subset of X capital A, then mu0 of capital A will be less than the Lebesgue measure of the volume of A, provided A belongs to X. So the choice, this particular choice of objective function here, its aim is precisely to ensure that measure mu0 has the largest possible support. Remember from the previous slide that we can prove that the support of mu0 is in the MPI, and so we want, in order to capture most of the information on X sub I on the MPI set, to make this set as large as possible. And we can do that with this LP, and this is the content of this theorem, and you will have to prove this theorem graphically for the second exercise. It's not too difficult to prove, actually. It's almost a drawing will do it. As soon as you understand a little bit the meaning of the support of a measure, it should not be a big deal. And the theorem says that this supremum actually is attained for a measure mu0, which is the Lebesgue measure, but on xi. So that since I take in the objective function the integral of mu0 over x, which is the mass of mu0, the value here, p star, is the volume of xi. So somehow, if I'm able to solve this linear programming problem on measures, I solve it with respect to mu0, and this slack measure here, mu0 hat, which I've not yet commented. This measure is just here, so it's a non-negative measure. It's just here to make mu0 less than lambda of x. It does not play any more sophisticated role. So the unknowns here are mu0, and mu0 hat. If I solve this problem and I look at the mu0 component of the triplet of optimal measures solving the problem, I get the uniform measure or the Lebesgue measure of xi. So that if I look at the support of mu0 star, I actually get xi, the set I'm interested in. Of course, this will be impossible since I'm not able to solve this infinite dimensional optimization problem and measures. But we'll see that thanks to the moment sum of squares hierarchy, we'll be able to approximately solve this problem with a family of convex optimization problems. So as I did the last week for polynomial optimization, I can construct the dual of the previous problem, so dual LP, and it looks like that. So it's an LP on continuous functions. The objective function will be the integral of one of the two variables of the dual. So there are two variables, v and w. Both are continuous functions on x. And the objective function is just the integral of v against the Lebesgue measure on x, so this quantity here. And the dual, the structure of the constraints follows actually by duality from the structure of the primal problem with the Liouville equation and the dominating equation. And I will comment on the structure of these inequalities later on. You can just observe that here, with no surprise, I get the Koopman operator, V composed with F. And the third exercise of the session will consist of deriving this dual from the primal using elementary notions of convex duality, as we saw last week. You build a Lagrangian, you build a Lagrange dual function, and you make this function explicit. By doing so, you will also be able to that there is no duality gap between these two problems, which means that D star here is equal to P star here in the primal. So I'm almost done for the first part, the linear formulation of my nonlinear problem. Just let me have a look at the structure of the dual a little bit more accurately. So here is the dual again. So observe first that from the structure of the problem, it follows that any dual feasible pair, VW, will be such that V will be non-negative and W will be bigger than 1 on X sub I, on the MPI set. So to prove this statement is rather elementary. So we just consider a trajectory X sub T in capital X. And we observe that the first equality just implies that V of x0 is bigger than alpha times f of, times V of f of x0, which is nothing but x1. So V of x0 is bigger than alpha V of x1. But then V of x1 is bigger than alpha V of x2. Hence, alpha V of x1 is bigger than alpha square of V of x2, and so on, until t tends to infinity, and alpha is between 0 and 1. This tends to 0 when t tends to infinity. Also because xt is in capital X and capital X in bounded, so that this quantity does not blow up. So this shows the first statement that on the positively invariant set, so this is precisely trajectory that remains in capital X, V is positive. And from the second inequality here, V is always bigger than V, sorry, W is always bigger than V plus 1. It follows that W of x0 is bigger than 1. Now, you see that the objective function consists of minimizing the integral of W everywhere on X. And W is bigger than 1 on Xi. So the intuition behind the dual problem is, we'll see that later on, that actually the it will make this as close to 0 outside of xi and equal to 1 precisely, or as close as possible to 1 precisely on xi. This is the intuition. And actually the proof of this intuition will be the contents of the last step, the step 3, the convergence of the hierarchy. But before that, let me get into the hierarchy. This will be very short. Step 2, convex hierarchy. So let me recall that I have 2 linear programming problems in duality, infinite dimensional. The first one involving 3 measures on X. The second one involving 2 functions, V and W, which are continuous on X. And hence, since X is bounded basic semi-algebraic and F is polynomial, all the data here are polynomial. And we can really plug and play the moment SOS technology, the device which I described last week. And we can use our favorite software, our favorite interfaces and solvers, semi-definite programming solver, to construct a family of approximations of this infinite dimensional problem. And these approximations will be finite dimensional convex optimization problems, semi-definite programs, for example, of increasing size. So remember from last week that actually what we do is that we replace this cone, the cone of non-negative continuous function on X, with this truncated quadratic module. You may remember that the quadratic module was indexed by 2 integers last week. It was just because we had finite degree polynomial whose positivity had to be certified. It was of degree D. And then we played with this relaxation order to build a lift of this difficult cone. Here, actually, we have to let the first index go to infinity as well, just because these cones are indeed genuinely dimensional. There is no finite dimensional convex formulation of the NPI set computation. So we let both indices here increase, and R will be this relaxation order. So in the primal, we'll get approximate or pseudo moments of the 3 measures in question. So there will be moments or approximate moments of degree up to R. And in the dual, we'll have polynomial sum of squares of degree up to R as well. So we'll get, by replacing C of X plus with Q of X R, we get a family of bounds on the objective function. Here, since we maximize, we get upper bounds, PR star on P star. And it turns out that there is no duality gap. P star is equal to D star. And also in the hierarchy, there is no duality gap. So PR star is equal to DR star. And in a dual, we'll get polynomial polynomial approximations of these continuous functions v and w that I will denote vr and wr. And now the last step of the program, step 3, will be just to prove that indeed when r tends to infinity, so the degrees of the polynomial tend to infinity, and actually these values converge to the value of the original program, which, let me recall you, is equal to the volume of x. And we'll see that we can get even more by looking at super level sets of V and WR. We'll get set-wise approximations. So this will be the last step, convergence. But before that, I'm ready to take questions, if any. So time for questions. So I get a question by Monique Laurent. Can you please repeat what is the first index R in the quadratic module? Yes. So Monique, you may remember that polynomial optimization was a problem of minimizing a polynomial P of finite degree D on the set capital X. And a way to do that was to just find the bigger lower bound on P, such that the graph of P is above the bound for all small x in capital X. And hence we had to deal with P of x minus the lower bound being non-negative on X. And what we did is to replace this non-negativity constraint, which is difficult to handle, with a simpler constraint, namely that P minus the lower bound was in the quadratic module. But since P was a finite degree polynomial, this was a truncated quadratic module. And the first index, D, in my notation of the quadratic module was the truncation degree of the quadratic module. So Q of X D sub R was a quadratic module truncated to degree D polynomials and approximated with sum of squares of degree generally bigger than D, and R is the degree of these sum of squares multipliers. So I hope this clarifies. Bernard Morin is asking whether the eigenvectors of the Frobenius-Perron operator are known. No, in general they are difficult to compute. There is a whole literature on approximations, numerical approximations of the eigenvectors. There is the dual counterpart, eigenfunctions of the Koopman operator, since the Koopman operator acts on functions. This is maybe even further and better studied, but there is a whole literature on that, on numerical schemes to approximate the eigenfunctions and eigenmeasures, and to approximate the spectrum, to know whether the spectrum is a point spectrum or whether it has a continuous component. So it's a whole world of many interesting questions. Are there further questions before I embark? Okay, Giovanni Fantuzzi is asking the following question. The primal and dual convex problem depend on the discount rate alpha. This cannot be optimized because it multiplies the unknown, measures continuous functions. Is alpha to be chosen arbitrarily If so, does the feasibility of these convex problems depend on the particular value alpha? That's an interesting question indeed. So for the infinite dimensional problem, there is no dependence on alpha, as you can see from the statements of the lemma and the theorem. So in terms of inclusion of the support of mu0 in xi, it doesn't change anything. In terms of the value of the prime and dual, which is volume of xi, there is no impact on alpha. Now, when it comes to discretizations and finite dimensional approximations of these problems, alpha will play a role. So it should not be taken too small. Alpha, something close to 1 is usually working well, but we don't have, let's say, a fixed policy for choosing alpha. Say something between 0.9 and 1 will do the job, but this is something to try out, and this will indeed have an impact on the relaxations and the behavior of the relaxations. Other questions? So the last part will be rather short, so don't hesitate to ask further questions during this last part. I will get back to them at the end. So let me get back to the last part. The convergence proof. Well, actually, I'm cheating a little bit because, of course, the formulation of the LP in the first step has been done in a very specific way, as you can imagine, so that indeed at the very end, convergence can be shown. So the convergence proof will be actually a mix, blend of all the ideas and techniques that we've seen in the first step. On the top of that, we'll of course have these classical arguments for convergence of the moment sum of squares hierarchy that we saw already last week. So sorry. So the primal LP was the following, and we saw already that was one of the theorem that the optimal value is actually the volume of the MPI set, and that it is attained by the uniform measure on the MPI set. So mu0 star, the optimal solution, mu0, is actually lambda of xi. For the dual LP, I started to argue that I shown actually that on the MPI set, W was bigger than 1. This I can phrase like that. W is bigger than the indicator function of the MPI set. So this function which is equal to 1 on xi and 0 outside. And since W is positive on x, this objective function is the integral of W respect to the Lebesgue measure on x is actually the L1 norm of W. So what I'm minimizing in the dual is the L1 norm of W. And we know that there is no duality gap, so that P star is equal to D star by strong duality. And hence that at the optimum, this L1 norm, this integral, must be equal to the volume of xi. But the volume is the integral of the indicator function of xi by definition. So that somehow W must be equal to the indicator function of xi for the dual value to be attained. However, the indicator function of xi is a discontinuous function, not a continuous function, so that in general, in the dual, the value is not attained. just because it's not possible to exactly model the discontinuous indicator function by a continuous function W. However, as you may imagine, it will be easy to construct a sequence, so-called minimizing sequence, of continuous functions W, such that this value here will be approximated as closely as desired. And since the objective function will be the L1 norm of W, this will be actually the argument behind the proof of convergence of the dual sequence in L1 or equivalently in volume to the MPI. So suppose the MPI is the -1/2 segment on the real line. So the indicator function here will be this function equal to 0 outside and 1, this is 1 here, inside xi, this is -1/2 plus 1/2. So here is an example of a minimizing sequence W indexed by the relaxation order R, such that the integral of W on the whole domain, here the -1, 1 interval, which plays the role of our set capital X, is as small as possible. So you see that here, I think I get a degree 4 polynomial, then it's a degree maybe 8 polynomial, then degree 12, maybe degree 20. I don't remember the exact numbers. What you observe when you try to make the graph of a continuous function here, a polynomial of increasing degree, to match from above as closely as possible the graph of a discontinuous function, what you observe here is these little ears here that cannot be reduced. This is called the Gibbs phenomenon, and this is something which is well known in numerical analysis. However, remember that the MPI set X sub I is such that on this MPI, W is bigger than 1. So that what really matters is the set of X such that the graph of W is bigger than 1. You see here, we get this set here, which is once projected down there, is this segment. And indeed, it's a valid outer approximation of the regional reduction, the MPI set, which is this -1, 1/2 interval. Here at degree 8, I get something which is even closer. You see, it's almost not seen on the figure. It's indeed a valid outer approximation, but extremely close already to the MPI set. And the larger the degree, the closer is the unit super level set of WR. So you see, minimizing the L1 norm of W will allow us to construct outer approximations of the set of better and better quality. So in substance, this is the content of this figure, and more rigorously, this is the content of this final technical slide. So if I replace the cone of non-negative continuous functions on X with this quadratic module indexed by the degree R, we get a sequence of bounds, which is monotonically non-decreasing, as we saw last week, and which converge indeed to the volume of the MPI set. So proof of that is not too hard with the Stone-Weierstrass theorem. This is one of the exercises you may try. And the last theorem is about guarantees in a dual. So in the dual, we obtain a sequence of polynomials VR and WR such that the zero super level set of VR is an outer approximation of Xi. I could have said the same for the unit super level set of WR, which was the contents of my previous slide. and in such a way that the volume of xi sub r tends from above to the volume of xi. Or in other words, if in xi r I remove xi, the Lebesgue measure of the set I get goes to 0 when r tends to infinity. So it's not too hard to prove this result neither. Essentially, this is the proof of L1 convergence from above of WR to the indicator function of xi. That's it. That's the end of the third step. So now I'll just illustrate it with a few examples. So I take only 2 examples. If you want more examples, there will be references. There are already references in the PDF file, which is attached to this lecture. You'll find references to the works we did on that, and this includes many more examples. So very quickly, this is another example of a quadratic map called the Catala system. So in gray, in dark gray, you have the exact MPI obtained by simulation. And in light gray, you have the super level set of degree 6 polynomial, which is a valid outer approximation of the MPI. And as the theory predicts, when you increase the degree of the polynomial, then you get a tighter outer approximation. And for the Julia sets, of course, things are much more complicated because of the fractal geometry of the objects in question. Here we took 2 examples of Julia sets. So Julia sets can be written as a quadratic iteration in a complex plane. So it's a 2-dimensional quadratic polynomial map if you replace complex coordinates with real coordinates. And there is a constant here. Depending on the constant, the geometry of the set of the MPI changes. It can be connected, and this is then called the field Julia set. Here it's obtained by simulation for the figure, or it can be disconnected. That was also the first example I started with. And of course, you see here in light gray the outer approximations of these MPIs with polynomials of degree 12. You see here that the geometry is such that it's very difficult for a degree 12 polynomial to very tightly, accurately include all these little guys. However, this is what we get, and the higher the degree, the better the approximation. In principle, when the degree tends to infinity, we have convergence in volume. Here, the volume is 0. The volume of the blue set is 0. So we get probably disconnected union of many very small components. It's very difficult to observe that numerically, just because the semi-definite programming problems are become very large, and also there are numerical scaling issues. Especially here, we use a monomial basis, which is not suited for high-degree computations. And it's certainly a very interesting research direction to try to improve the numerics of this kind of set computations. With that, I would like to conclude this second lecture. Thank you for your attention. And I'm ready to take further questions for this lecture. And after that, I will get back to the questions and exercises of the first lecture as promised. Further questions? No question this time. Anything known about the convergence rate of the bounds? Yes, I think we have. That's asked by Monique, Monique Laurent, who is an expert in the convergence rate of hierarchies. We have convergence rates, but not for MPI or regional attractions of dynamical systems. We have convergence rates for computing the volume of a semi-algebraic set. And the computation of the volume of a semi-algebraic set, of a given semi-algebraic set, capital X, the idea is the same as the one we saw today for MPI. So it means that this will be the way to go in order to get convergence rates for these problems, to somehow extend the ideas we have already for the volume computation. Thanks, Victor Magron, for giving the link to the volume approximation paper. The convergence rates now for the volume approximation is based on an analysis that was done by Markus Schweighofer and Jiawang Ni. I think that Victor Magron provided the link to this work last week as well. It's called the Complexity of Poutinar's Positive Channel Sets. I don't know the exact title, but I'm sure you'll find it on the web. And basically, for the volume approximation, the rate is rather pessimistic. It's log of 1 over r, which is very slow in practice. What we observe numerically for volume computation is indeed sublinear rate of convergence. This rate can be improved in the case of a semi-algebraic set X, whose volume must be computed. If the semi-algebraic set is defined by a single polynomial superlevel set, it's log of 1 over r. But probably we cannot go. We cannot improve that much better. This is the kind of convergence rate I expect for the MPI set approximations. Victor Magron also, yes, thanks, Victor, gives you a pointer to the convergence rate analysis for optimal control. This is the topic of the next lecture. We'll apply the moment sum of squares hierarchy to approximate the value function of optimal control or ordinary differential equations, and there we could get, it's a joint work with Milan Korda and Colin Jones, we could get convergence rates for these problems, and they are of the same nature, log of 1 over r. Bernard Morin is wondering whether the approach can be applied to approximate other type of sets and graphs. Yes, well, partially in the previous question answer. Yes, indeed, similar ideas will be used next week to approximate the value function of optimal control. I had tried a few years ago to approximate solution of shape optimization problems with these techniques, but I must say that I did not succeed. I guess that indeed the other type of difficult sets graphs you want to approximate could be attacked with these techniques, and then the question arises of whether it could be competitive with respect to the state of the art. Maybe Bernard, you have a specific set in mind you want to compute approximately? So I can still give you a few more minutes for questions on this second lecture. Giovanni Fantuzzi, thanks for asking, is wondering whether there are difficulties for extending the analysis to continuous time systems, especially in terms of convergence results. Actually, this was the starting point of the work we did on discrete time systems. So it's a joint work. I'll give references in the written lecture notes. But this is joint work with Milan Korda and Colin Jones at that time. Actually, we started with continuous differential equations, and we were interested in finite time region of attraction problem. And then we extended these ideas to infinite time region of attraction and also discrete iterations. So there are difficulties for all these extensions, and but in many of the cases we could somehow tackle them. Discount factors were very important for asymptotic results, as you saw already today. So Wang is asking what is the advantage or disadvantage of the LAAS hierarchy approach in finding the approximation of the volume of invariant set compared to other methods in theoretical and practical respects. It's true that we have not done systematic comparison with alternative numerical methods. There are many competing algorithms for set invariants, especially in control. Let's say that with this LAAS hierarchy, we are still facing the issue of dimensionality. So the fact that the method does not scale well with respect to the number of states. So if you have more than, say, 8, 9 states, so it's the size of n, the size of x, which was denoted by n in the lecture, then you can solve only the first few convex optimization problem in the hierarchy. So this is the case of many other methods for set estimation, set approximations, maybe, I know, those based on interval analysis, they will suffer the same kind of issue. So our method is no exception, unfortunately. And as this has been discussed a lot last week, there is still hope that we can exploit the problem structure, symmetries, and sparsity in the context of NPI set estimations to get a little bit farther. So currently the PhD thesis of Matteo Tacchi, funded by RTE company and hosted by our lab in Toulouse. This PhD thesis is precisely focusing on the sparse regional attraction problem, where we have a problem similar to NPI set estimation, but for continuous time systems. And we assume that the dynamics, the FMAP, has some kind of sparsity. And we try to go further in terms of number of variables. So this is ongoing work. We can also add that there is also an attempt currently also ongoing work with Tillman-Weisser as well, about computing the volume of a sparse semi-algebraic set. So high-dimensional, maybe n by the tens, by the hundreds. But the defining polynomial of x, this j sub k of x, they have some sparsity pattern, and try to figure out whether we still can compute approximately the volume using these ideas. So I'll give pointers to the references in my written notes attached to the lecture. Thanks for asking. Alejandro González Nevado wants to know whether another outer measure, not Lebesgue, maybe Hausdorff, can be used to compute the volume of the set, of the MPI set, so that we can design iterative methods converging in this other measure. Yeah, well, if instead of the Lebesgue measure, the volume is a Lebesgue measure, you want another measure, maybe the Gaussian measure of a set, indeed, you just have to modify this right-hand side in the LP problem. And there may be some additional difficulties to deal with, but basically, in principle, you can try to carry on this program and go and see what you get. What probably is out of reach, at least for MPI set estimation, is a stronger notion of convergence. For example, convergence in the Hausdorff metric of sets. This would be much more. So as I see it, convergence in Lebesgue measure or in volume is in the functional side corresponding to L1 convergence. Convergence in the Hausdorff measure sense would be convergence in L infinity, uniform convergence. And this is probably too hard to achieve unless you know in advance that the MPI set has some regularity property on its boundary. So you saw with simple examples of quadratic maps on the plane that the MPI set can be very, very complicated. It can be fractal. So L1 is the best we can do without further assumption on the geometry of the boundary. Okay. So now, as promised, now I will go quickly through the solutions of the exercises for the last lecture, for the first lecture. So I share my screen again, and I will just show you the PDF file and comment it. You have this PDF file on the website of POEMA, and you can browse through it as well offline if you're interested. So let me share the screen and show you these notes. So these are notes corresponding to the first lecture. As I said, there will be notes for the lecture of today and also for the lecture of next week. And so in these notes, you can find references to the literature. You can find the statement of the exercises as given during the presentation. And you can also find the chat, the questions and answers to the questions during the chat. So for the exercises, the first exercise for polynomial optimization was to prove that actually if you replace a polynomial optimization problem, this one, with a linear program on probability measure, the values are the same. So V star is equal to P star. And so for that, the intuition is that actually the solution of the problem on measures actually is a Dirac measure supported on any globally optimal solution of the original POP. And the proof is more or less that. So you can see it's only a few lines. Basically, one direction is just obtained by restricting the measure to be the Dirac measure at any global optimizer. And the other direction is almost, by definition, of a global minimum. So I will not comment it further. It's the simplest proof one can think of. As to the second exercise, it was about applying convex duality to derive this LP, the dual LP from the primal one. And in order to do that, we just proceed as described in the slides. So we just build the Lagrangian. So Lagrangian is just the primal objective function plus a weighted sum of constraints where the weights are dual variables or Lagrange multiplier. So you see here the constraint, the only constraint, which is this mass equal to 1 constraint. The multiplier is the scalar, since this is a scalar, a real constraint. And then we have the conic constraint, which says that the duality between mu and the second dual variable or continuous function, W, appears here with the appropriate sign. And then you construct the dual Lagrange function by minimizing respect to the primal variable, the Lagrangian. You obtain this, and then you argue that it is bounded below only if this term vanishes. And then the dual LP follows readily. It's really just following the steps outlined in the slides, you get it. The interpretation of the dual is that, as been mentioned already several times, is that it seeks the largest lower bound on the graph of P on X. If you like duality of infinite dimensional linear programs, you can also use a result which you can find in the theorem in the textbook by Sasha Barvinok on convexity. And the result says that there is strong duality whenever the image of the cone through the linear objective function and the constraint, so this two-dimensional set will be closed. So this is an alternative proof of strong duality. This closure of the image of the cone in the primal problem is also used to prove strong duality for MPI LPs and also regional refraction LPs. This is very handy. The third exercise was about showing that deciding whether a polynomial is squares of other polynomials is actually can be reduced to semi-definite programming. So in order to prove that, you just use your favorite basis for the vector space of polynomials of n variable of degree d. I denote this basis by bold B. And then every polynomial of x of degree up to d can be written as a linear combination of elements in this basis. This is denoted by this inner product. So polynomial S will be a sum of squares. By definition, whenever it can be expressed as a finite sum of squares of polynomials. And so then if you express these polynomials as linear combinations in the basis B, you just get that, which can be rearranged. And the basis appears now quadratically and can be outer factorized. And what remains here in the middle is a matrix, which is the sum of these rank 1 terms corresponding to coefficients of the PIs. This matrix is positive semi-definite by construction. It's called a Gram matrix. And deciding whether polynomial S is a sum of squares actually amounts to finding a matrix S, which is positive semi-definite, and whose entries is linearly related to the entries, to the coefficients of S. So it's a semi-definite programming feasibility problem. That's the proof. If you prefer to view it geometrically, the source cone is a projection of the semi-definite cone. The fourth exercise was about describing explicitly the dual of the truncated quadratic module. So this is the quadratic module that Monique Laurent was wondering about, this, with the two indices. So the first index D is the degree of truncation of the quadratic module. So it's a cone which lives in the vector space of polynomials of degree up to D. But in order to represent an element in the cone, I may have to use a sum of terms whose degree is R, with R bigger than D. And typically R can be much bigger than D. This is why geometrically you can view this truncated quadratic module as a projection of the sum of squares cone, since each term here in the weighted combination is the sum of squares of finite degree, ruled by the degree of each product. So it can be viewed as a projection of the source cone onto a finite dimensional and usually a smaller dimensional vector space. So that was a definition of quadratic module, truncated quadratic module. And the question was about finding an explicit formulation of the dual quadratic module, which was the outer approximation of the cone of moments as a projection of a linear slice of the semi-definite cone, as a projection of a spectrohedron. So way to look at that is to define the image of the sum of squares cone times a factor here, a GK factor. The polynomials are rising in description of X. So that's again a projection of the source cone. And to write, just follow up the definition here, to write this geometrically as a weighted sum with the weights are these polynomials of the sum of squares cone. To write the truncated quadratic module like that, where the sum here in the sum in the summation denotes the Minkowski set addition, so the element-wise addition. So by duality, this dualizing here replace this Minkowski sum by an intersection of what? Of dual two projections of source codes. So now each of these cone here can be written explicitly again by expressing elements in this cone as a combination of coefficients in the basis B. So this is what done is here. The dual cone is precisely the set of all linear functions which are non-negative when they act on the primal cone. And now we can express this in the basis like that. And then I have a vector corresponding to sum of squares, decomposition of Q, which I denote by bold P, and eventually positivity of the form becomes positivity of quadratic form, and so that I can get rid of the quantifier for all P by looking at this here matrix corresponding to the quadratic form. So this matrix has a name. It's called the localizing matrix. And when k is equal to 1, this is what we call the moment matrix. And hence that this dual cone can be seen as the set of moments such that the localizing matrix is positive semi-definite. So in the space of moments, this is defined as a linear matrix inequality, or in other words, a spectrohedron. So this is a way to prove this statement that the dual cone is a projection of spectrohedron or a linear matrix inequality. The last exercise was about proving that in the hierarchy, when now we plug in, instead of our positive polynomial and moment cone, we plug their relaxation with a quadratic module, that strong duality holds for all R. This is rather easy when capital X, the set over which optimization is done as a non-empty interior, because then it's easy to prove that this primal problem has a non-empty interior. It's enough to take any sequence of moments supported on sufficiently many points in X. Since X has an interior, you can take as many as you want. If S has an empty interior, or if X is empty, still you can prove strong duality, but then the argument is a little bit more complicated. And actually, it relies heavily on the assumption that one of the polynomial make the quadratic module Archimedean. So one of the polynomial, for example, has this form. So if you want to find a detailed proof of that, you have to go to the technical literature. That's it. And then you see there is a third part here with all my written answers to the questions that were given during the first lecture. There are plenty of them. And I tried to put references to literature I know of. So of course, if you find mistakes or if you want to iterate further on these answers, I would be happy to update this document. That's it. So let me get back to the chat now to see if there are further questions. So further questions for one or two.
Thanks a lot, Didier, for your nice presentation and also the material you provide. So this material is also available from the website of POEMA. I think everyone get the link. And so we see you next week.
Indeed. That's it. So
Wednesday.
And the last lecture I will give, there will be more lectures to come, but by other people. The last lecture I will give will be about using these techniques to approximate the value function of the controlled ordinary differential equations.
Thank you.
You're welcome. Thanks for your questions, for attending, and see you in a week, hopefully.